put a charged particle here, another charged particle over there. They push each other apart. Simple, right? Wrong. Here's what you just said without realizing it. Something invisible reaches across empty space, knows exactly how far away the other charge is, calculates the right amount of force using the inverse square law, and pushes. You're describing action at a distance, instantaneous communication across a vacuum. That should bother you. It bothered Newton so much he called it absurd. And Newton invented gravity, another action at a distance force. So when Newton calls something absurd, you should pay attention. But here's the real question, the one that exposes how little you actually understand. What's in the space between those charges? Nothing, you say. Empty space, a vacuum. Then how does the force get across? You've experienced electric fields your entire life. Every time you shuffle across carpet and shock a doorknob, every time you see lightning, every time a nerve fires in your brain right now while you're reading this, electric fields are doing all of that. You've seen their effects thousands of times. But what are they? Not what do they do? What are they? You can't answer that. Nobody can. Not completely. But here's what we can do. We can track exactly how physicists went from mysterious force reaches across space to space itself is doing something to there's energy stored in empty space to the vacuum is seething with virtual particles to, well, we'll get there. Think about this. Take two charges, separate them, measure the force between them. Now do something simple. Move one charge. How long before the other charge feels it? Your intuition says instantly. Move this one. That one responds. That's what action at a distance means. Your intuition is wrong. The speed of light, 299,792,458 meters per second, isn't just about light. It's the speed of causality itself. It's how fast changes in electric fields propagate through space. Move one charge and the other charge doesn't know about it until the field disturbance travels across at light speed, which means there's something in the space between them, something that can carry information, something that stores energy, something that has properties, energy density, momentum, angular momentum. So what is that something? Go get two magnets, strong ones. Push them together, like poles facing each other. Feel that resistance? That's not magic. That's not one magnet knowing the other is there. That's you doing work against the magnetic field in the space between them. That field is real. It has energy. You're adding energy to it by compressing it, just like you add energy to a spring by compressing it. Now pull the magnets apart. You get that energy back. Where was it stored? In the field, in the empty space between the magnets. Here's the thing nobody tells you. That empty space isn't empty. Not if it can store energy. Not if it has properties. Not if changes in it propagate at a finite speed. So let me ask again, what's in an electric field? The first answer, the one that seems to explain things but actually just relabels the mystery, is field lines. You've seen the pictures. Iron filings around a magnet making beautiful patterns. Textbooks love these diagrams. They draw lines radiating out from charges, nice and neat, and they say the field points along these lines. Fine, but what are the lines? Are they real? Are they physical objects? No, they're a visualization tool, a way to represent the direction and strength of the field. The field isn't made of lines any more than a mountain is made of contour lines on a map. The lines are useful, they're not the thing itself. This is where most explanations stop. They give you the mathematical description. The field at any point is a vector, it follows Maxwell's equations. You can calculate the force on a test charge, and they act like that's an explanation. That's not an explanation, that's a description. It's a very precise, very useful description. But it doesn't tell you what the field is. Feynman knew this. He spent years thinking about it, teaching about it, being frustrated by it. Here's what he concluded. At some point, the chain of explanation ends. We reach something fundamental that we can describe perfectly, predict perfectly, but can't reduce to anything simpler. The electric field might be one of those things. But before we accept that, let's trace how we got here. Because the history isn't just interesting. It reveals exactly where our understanding deepens and where it hits bedrock. Michael Faraday invented the concept of the field in the 1840s. Not the mathematics of it. He barely knew calculus. The concept. He was playing with magnets and electricity. And he noticed something. The space around magnets and charges behaves like it has structure. Move a compass near a magnet, it points in specific directions. The directions make patterns, continuous patterns, that fill all of space. Faraday called these patterns lines of force, but he meant something physical. He thought correctly. It turns out that something real was happening in the space itself, not action at a distance. Action right here, mediated by whatever occupies this point in space, which then affects the next point, which affects the next point, and so on. This was radical. The dominant view was Newton's. Forces just reach across space, instantaneously. That's how gravity works. That's how everything works. Faraday said no, there's a medium, the force propagates through the medium. Then James Clerk Maxwell came along in the 1860s and turned Faraday's intuition into mathematics. He wrote down 4 equations, Maxwell's equations, that describe exactly how electric and magnetic fields behave. And here's what those equations revealed. Electric and magnetic fields aren't separate things. They're 2 aspects of the same thing, the electromagnetic field. Change an electric field, you create a magnetic field. Change an electric field, you create a magnetic field. They're coupled, interlinked, inseparable. More than that, Maxwell's equations predicted that disturbances in the electromagnetic field should propagate as waves. And when Maxwell calculated the speed of those waves from his equations, he got 299,792,458 meters per second, the speed of light. Think about what that means. Light isn't a separate phenomenon. Light is electromagnetic waves, oscillating electric and magnetic fields, propagating through space, carrying energy and momentum. Maxwell realized this in 1865. He predicted electromagnetic waves before anyone had detected them. Heinrich Hertz confirmed it experimentally in 1887. He generated radio waves in his lab, detected them across the room, and showed they traveled at the speed of light. So now we know the electromagnetic field is real. It's not just a mathematical convenience. It carries energy. It transports momentum. It propagates at a finite speed. You can generate waves in it and detect those waves. But that still doesn't answer the question, what is it? Maxwell thought, like Faraday, that there must be a medium, some substance filling space that vibrates when electromagnetic waves pass through. They call it the luminiferous aether. Solid enough to transmit waves at the speed of light. Tenuous enough that planets pass through it without resistance. This aether was supposed to be everywhere. The fabric of space itself. And if it existed, you could detect it. Because Earth moves through space around the sun, around the galaxy. So we must be moving through the aether. Which means the speed of light should be different in different directions. Faster when you're moving with the aether. Slower when you're moving against it. Albert Michelson and Edward Morley tested this in 1887. They built an interferometer sensitive enough to detect tiny differences in the speed of light in perpendicular directions. They measured. They found nothing. No difference. Light travels at the same speed in all directions, regardless of how you're moving. The ether doesn't exist. So what does that leave us? Electric and magnetic fields are real. They carry energy. They propagate. They do things. But they're not vibrations in a medium. They're not made of anything we can point to and say that's the substance of the field. This is where Einstein walked in 1905 and changed everything. Einstein said, forget the ether. The electromagnetic field is fundamental. It's not made of anything else. It's a basic property of space-time itself. And here's the key insight. Space-time isn't just an empty stage where physics happens. Space-time itself is dynamic. It has properties. It responds to what happens in it. In special relativity, space and time are unified into space-time. Electric and magnetic fields are unified into the electromagnetic field. And this field is a property of space-time. It's how space-time responds to the presence of charge. Put a charge here, space-time develops a structure around it, the electric field. This structure tells other charges how to move. Change the field here, and the change propagates through space-time at light speed, affecting other charges only when the disturbance reaches them. But Einstein wasn't done. In 1915, he published General Relativity, which revealed something deeper. Space-time itself is dynamic. Mass and energy curve space-time, that's gravity. And the electromagnetic field has energy, so it contributes to the curvature of space-time. This creates a beautiful, strange loop. The electromagnetic field is a property of space-time. But the electromagnetic field has energy. Energy curves space-time. So the field affects the very space-time that defines it. Let me put some numbers on this to show you it's not just philosophy. Take 2 electrons 1 meter apart. The electromagnetic force between them is about 2.3 circumflex 28 newtons. Tiny, right? Now consider the gravitational force between those same 2 electrons. It's about 5.5 circumflex 71 newtons. The electromagnetic force is 10 circumflex 42 times stronger than gravity for these particles. 10 trillion times stronger. If gravity were a single person, electromagnetic force would be every human who ever lived, times every star in the observable universe, times 1 billion. So when we talk about the electromagnetic field storing energy, we're not talking about some negligible effect. We're talking about the dominant force in everyday physics. Chemistry is electromagnetic. Biology is electromagnetic. The structures of matter, solid, liquid, gas, are determined by electromagnetic forces between atoms. Every time you touch something, you're not actually touching it. The electrons in your fingertips are repelling the electrons in the object through the electromagnetic field. The field is doing the pushing. You've never touched anything in your life. You've pushed against fields. Right now, the neurons in your brain are firing. How? Electromagnetic fields. Voltage-gated ion channels open and close in response to electric fields across cell membranes. The field strength? About 10 million volts per meter. That's stronger than the breakdown voltage of air. Your neurons are operating in conditions that would cause lightning if they were scaled up. The electromagnetic field isn't some abstract physics concept. It's the mechanism underlying basically everything you experience. But here's where it gets truly strange. Quantum mechanics enters the picture in the 1920s and changes everything again. In quantum field theory, developed by Paul Dirac, Richard Feynman, Julian Schwinger, and others in the 1940s, the electromagnetic field isn't just a classical field that smoothly fills space. It's quantized. It comes in discrete packets, photons. A photon is an excitation of the electromagnetic field, a ripple, a quantum of energy in the field. When you detect a photon, you're detecting a localized excitation in the electromagnetic field. But here's what nobody tells you. The field is still there even when there are no photons. The quantum electromagnetic field has a vacuum state, its lowest energy state, and that vacuum state isn't nothing. It's seething with activity. Virtual photons constantly pop into and out of existence. These aren't real photons. They don't last long enough to be detected directly. But they have real effects. They contribute to the electromagnetic force between charges. The force isn't just particles exchanging photons like tennis balls. It's a continuous interaction mediated by the quantum field, including all those virtual photons flickering in and out of existence. We've measured this. The Lamb shift, a tiny splitting in the energy levels of hydrogen, is caused by virtual photons interacting with the electron. We calculated it using quantum field theory. We measured it. They match to absurd precision. The Casimir effect is another example. Put two metal plates very close together in a vacuum. The quantum vacuum between them has fewer virtual photon modes than the vacuum outside. This creates a pressure difference. The plates attract each other. This was predicted in 1948. It was measured in 1997. The theory and experiment agree to within experimental error. So the empty space in an electric field isn't empty. It's full of virtual particles, quantum fluctuations, zero-point energy. The vacuum has energy density, about 10 circumflex, 113 joules per cubic meter, according to naive quantum field theory calculations. That number is wrong, obviously wrong, because if it were right, the universe would have collapsed or exploded instantly. This is called the cosmological constant problem, and it's one of the biggest unsolved problems in physics. Our best theory predicts a vacuum energy 120 orders of magnitude larger than what we observe. We don't know why. We don't even know if we're asking the question correctly. But here's what we do know. The quantum vacuum has measurable effects. It's not just mathematics, it's physical. You can measure it, you can test predictions about it, and every test we've done confirms that the vacuum is something, not nothing. So let me take you back to the original question. What's in an electric field? Energy, measurable energy that you can calculate, that you can detect, that does work. The energy density of an electric field is E phi doro E query 2, where E is the field strength and E phi doro is the permittivity of free space. This isn't abstract. Put a charge in the field, it accelerates. Where does the kinetic energy come from? The field. The field had energy. The charge gained energy. Total energy is conserved. Structure. The field has a direction at every point in space. It has magnitude. You can map it. It has continuity. Change the field here. Nearby regions change smoothly. It has dynamics. Maxwell's equations tell you exactly how it evolved. Quantum fluctuations, virtual particles, zero-point energy. These aren't just theoretical constructs. They have measurable effects on real particles in real experiments. But also, and this is crucial, we don't know what it's made of. We can describe its properties perfectly. We can predict its behavior to 12 decimal places. We can use it to build GPS satellites that account for relativistic effects on electromagnetic signals. We can use it to design particle accelerators that bend beams of charged particles with magnetic fields. But we can't reduce it to something simpler. This is where the chain ends. The electromagnetic field is fundamental. When you were a kid, you probably asked why over and over. Why is the sky blue? Because of Rayleigh scattering. Why does Rayleigh scattering happen? Because light is an electromagnetic wave and molecules are smaller than the wavelength. Why does that cause scattering? Because the oscillating electric field induces dipoles in molecules which re-radiate. Why does the field induce dipoles? Because electrons respond to electric fields. Why do electrons respond to electric fields? Because they're charged. Because they interact with the electromagnetic field. Why do they interact with the electromagnetic field? Here's where I have to tell you something that might frustrate you. That's where the explanation stops. Not because we're ignorant, not because we haven't thought hard enough, but because we've reached bedrock. Electrons interact with the electromagnetic field. That's fundamental. That's what charged means operationally. It means couples to the electromagnetic field. There's no deeper answer. Not yet, maybe not ever. And that's okay. Understanding doesn't mean infinite regression. It means reaching the fundamental principles, knowing which principles are truly basic, and being able to derive everything else from them. We can derive all of classical electromagnetism from Maxwell's equations. We can derive all of quantum electrodynamics from the principle of local gauge invariance. We can calculate the magnetic moment of an electron to 12 decimal places and measure it and watch them agree exactly. That's understanding, real understanding. Not mystical insight into the ultimate nature of reality, but precise predictive power grounded in measurement. Let me challenge your intuition one more time. You look at your hand. It's solid, substantial, made of atoms, sure, but ultimately made of stuff, particles, things. Wrong. Your hand is a pattern of excitations in quantum fields. The electrons aren't little balls orbiting nuclei. They're ripples in the electron field. The quarks making up protons and neutrons, ripples in the quark fields. The electromagnetic forces holding atoms together, ripples in the electromagnetic field, photons being exchanged between charged particles. You're not made of stuff, you're made of fields. Structured patterns in fields. Stable configurations that persist because the physics makes them stable. The electric field between the electrons and protons in your body isn't empty space with a force reaching across it. It's a region of space-time with a specific energy density, a specific structure, specific quantum fluctuations, and that structure is doing the work of holding you together. Right now, every moment. Think about that for a second. Everything you call matter is field configurations. Everything you call force is field interactions. The distinction you think exists between substance and force, between matter and energy, between particles and waves, these distinctions dissolve when you look carefully. There's just fields, quantum fields, interacting, creating stable patterns we call particles, exchanging quanta we call forces, evolving according to equations we've discovered and tested and found to be correct to preposterous precision. The electric field isn't something separate from reality, reaching across empty space to push charges around. The electric field is reality at that point in space. It's what space-time is doing there. And what it's doing includes storing energy, carrying momentum, supporting quantum fluctuations, and mediating interactions between charged particles. We started with a simple question. Put two charges in empty space. They push apart. What's in between? Now you know energy, structure, quantum fluctuations. Space-time doing something specific, something measurable, something we can calculate precisely and test experimentally. Is that all there is to it? Probably not. Quantum field theory and general relativity are both incomplete. They contradict each other at extreme scales inside black holes at the moment of the Big Bang. We need a theory of quantum gravity to go deeper. Maybe when we have that theory, the electromagnetic field will turn out to be made of something else. Vibrations and strings or loops in space-time or something we haven't imagined yet. Or maybe the electromagnetic field really is fundamental. Maybe we've hit bottom. Maybe this is where physics ends and mathematics begins, not because reality is mathematical, but because mathematics is our tool for describing the patterns we find in reality. Either way, here's what I want you to take from this. The next time someone tells you opposite charges attract, don't just nod. Ask them why. Ask them what's between the charges. Ask them how the force gets across. Ask them about the field. Ask them what the field is made of. Ask them where the chain of explanation ends. Most people will give you comfortable lies, vague words, hand-waving, metaphors that obscure rather than clarify. But now you know better. You know that electric fields are real, physical, measurable things. You know they carry energy and momentum. You know they're quantum objects with fluctuations and zero-point energy. You know they're fundamental, possibly irreducibly fundamental. You know what we understand precisely and what remains mysterious. You know the difference between description and explanation. You know where one ends and the other begins. That's what physics is. Not certainty, not comfortable stories. Truth. And truth is always stranger than fiction, but more satisfying, more precise, and infinitely more useful.